Hello again. Let's wait for a minute for more participants. Let me check again that I'm recording my voice as well. Yes. All right. Okay, so let's continue. So this is the picture that we are given. We are given the camera, the vectors u, v, and the gaze direction. The left, right, bottom, top boundaries are image window, and the distance of the image window to our focal point, and the angle that it makes, the angle that our gaze makes with the image plane is 90 degrees. So the image window is orthogonal to our gaze. In different settings, this is not necessarily so. You may actually want different views for different effects, but this is the most standard view, standard setting of a camera. Now, given our goal is this, we want to have a function in which we'll take the pixel coordinates as input. So I and j are going to be given to us as input. Sorry, this doesn't look like j. So I and j is going to be given to us as input, which may change from 0, 0 to nx minus 1, the final largest indices that we are going to have are nx minus 1 and ny minus 1 if we have 0 based indexing and nx times ny pixels. So given an integer pixel coordinate, our goal is to find the xyz coordinate of this point on the in real world, in the world coordinate system. So that's our goal. So here we will first start by finding the coordinate of this point. So what we will be doing is this. Let's call this point Q. We will find the coordinate of this top left point of the window. After that, if this is I, as you can see, this is I is actually going to be R in the X coordinate system. It's not going to be like array-based indexing. Okay, so I think I'm still not sure. I'm going to show you the equation in a couple of minutes. But what we are going to do is, after we find this point, based on what I and j is, we are going to figure out how many units. We are going to find this distance. Again, in terms of positive distance this time, we are going to call them SU and SV, which is going to indicate us the distance in world units from this point Q. So we will be doing this. If you have this point Q, if you go SU units in the U direction, okay, so U is the vector, this SU is a scalar. If you go in the U direction, SU units, and if you go in the minus, if you look at this down direction, what is this down direction? It's minus V, right? So minus V. Minus V is this down direction. V is the up vector, as you can see. So if you go in the minus V direction, SU units, so plus SV. So okay, so if you find this SV, if you find this distance and this distance, the coordinate of the center of this pixel will simply be Q plus SU plus SV minus V. What is SU? It's not difficult to guess actually. For example, if I is 0, I'm at the pixel 0 here. What is SU? You can write in the chat box. And also, what is SV? For this point, for this pixel 0, 0, what is SU and SV? Which is this? This is SU, this is SV. Actually, it's clear, right? SU is half pixel width, SV is half pixel height. Okay, if I have pixel height and pixel width as PH and PW, this is pixel width, SU is going to be 0.5 times pixel width, and SV is going to be 0.5 times pixel height for this pixel 0, 0. For each new I mean, if I'm at coordinate 1, 1 here, I'm going to be adding what? 1 pixel height, 1 pixel width. So depending on your I and j coordinate, if your I is 1, you're adding to this whatever your I is plus the pixel width. Okay? So that's basically the equation we have. Whatever your j is, you're going to be adding the pixel height to that. Okay? Because at 0, 0, it was this. When I is 1, I need to go another pixel width to the right. When I is 2, I need to go another 2 pixel width to the right. So this is the equation we first figured out. It's really simple, right? 0.5 pixel width. I mean, we can actually take this into parentheses of pixel width. 0.5 plus I times pixel width. That's the equation for this SU and SV. And as I said that U and minus V are already given. If I go from this point Q, if I go SU units in the U direction and SV units in the minus V direction, so this is a multiplication actually. I'm going to erase these writings on the slide so it will be clear. But if it basically says if you go SV units in the minus V direction, you will end up at the coordinate of the center of this pixel. So it's this simple. The whole equation is this. And now let's come to our question. What is Q? What is the top left corner of this image plane? Because if I have that, my equation to find the center of this pixel is really easy. All I need to do is find this SU, SV based on I and J, which is real simple. Pixel width. What is pixel width? R minus L divided by NX. What is pixel height? T minus B divided by NY is my pixel height. So pixel height and pixel width are also given. If I multiply them with this, I have my SU and SV values. What is Q? How do we find Q? Actually, for Q, we will be using this middle point. Q is also very easy. If you go from the middle point in this direction, how many units? L units. This is what L was for, right? L was showing from this center how many what is their sign distance. So in other words, what I'm going to be saying is that Q is simply equal to M plus L times U plus what? Can you tell me what it is? Okay, if I go L units in this direction, I find myself here. Now I need to go where? I need to go up. Okay, how many units? Exactly, T times V. This is exactly what Q is. If you go in the U, but we have to go in the minus U direction, right? But why did I not write minus U here? Because L is signed. Exactly. That's perfectly right. You got it. So L is already negative. So therefore it's the sign distance. You have to go in the U direction in L. Therefore L is minus 2. If you multiply minus 2 with U, it tells you that you will be here. Okay. Then if you go in the V direction T units, you will find yourself at Q. So perfect. We have found what Q is. We know how to figure out SU and SV. The only thing that we don't know yet is M. And also it's going to be very simple. What is M? What do I need to do? E plus, can you tell me what it is? E plus minus W distance, right? We already talked about this in the previous lecture. So if you start from E and go in the minus W direction, distance units, you're going to find yourself at M. This is what M is. So we have figured out the whole formulation is this. This is distance. So this is what we're going to do. Given any ij, I know what E is. The first thing is I'm going to compute M. This is a camera parameter. This is a camera parameter. This is a camera parameter. vector. So m is actually fixed. I can actually store this m with my camera because there's nothing here that depends on I and j. Same here. There's nothing at q that depends on I and j. So I can pre-compute this m and q and store them with my camera because they are constant. M and q for this image camera model, they are constants for me. There is nothing relating to for every pixel they will be the same. Whatever ij is, m and q are always the same. So a given ij, what I will first do is I will compute this su and sv values, which are scalars, by the way, and they're positive. Okay, if you look at this pixel width, pixel height, they're all positive. ij are positive in image coordinates, and this su and sv will be positive distance values that will show you your distance in terms of world units from q. After you compute su and sv, just add su times u, which is this will be a vector. Okay, you're scaling the u vector, which tells you you're going in the horizontal direction with respect to the image plane. And this u, by the way, is not always 1, 0, 0. Okay, I mean, u can be, for example, if you have a camera that is looking this way, sideways, u actually is 0, 1, 0. So going in the row, if your image pixel coordinates increases in row in its u direction, what happens? They actually had to increase in y coordinates in the real world coordinate, right? That's actually reflected right here. Whatever u is, you don't care about that. U shows correctly the direction of a row of your image. So go in the u direction, SU units, and go in the minus v direction, SV units. You're going to find your pixel center. That's it. So it's not. I mean, if the equations are really simple, if you know your vector algebra, if what happens, you start from a point, you go in a certain direction, certain units. Actually, all of the computations we have done here are very similar to the parametric line equation, right? Starting from a point, going in a direction, certain number of units. It's exactly the same. Nothing different. We didn't use anything different than the ray equation already. In order to find m, we have started from E, went distance units in minus W direction. In order to find Q, we started at M, went this direction, and then went up. Okay, these are just vector additions. And then from here, we have to then go based on what I and J is, SU units in the U direction and SV units in the minus V direction. That's it. So I'm going to erase this ink so we can have nicely written formulas there. Yeah. Okay, so if you go over the slides again quickly. So M is this. This is what exactly I wrote. Q is equal to M plus LU plus TV. And S simply will be Q plus this SU units U is minus SV units V. So it's exactly the same thing I had written with my hand. How do you find SU and SV? This is exactly what they are. R minus L divided by NX. What is this? This is my pixel width. This is my pixel height. And therefore, since this becomes SU, we go I units here. It also tells me that, so what was the correct one? Do I use my image coordinates as if I access them as array indices generally, or as if they're XY coordinates? I actually use them as if they're XY coordinates, right? I mean, an image, sorry, let me get to the interruption again, pen again. So an image coordinate ij does not mean that I'm at the ith row and jth column. It's actually vice versa. I indicates the pixel here, the ith pixel if you go from left to right. I is the column value. So this is I, this is j. This is what I'm saying. When we are given a pixel coordinate like this is I, this is j. In terms of array indexing, it's like ji, right? I mean, that may be confusing, but I understood this now because I looked at this. If you go in the u direction, the I coordinate, image coordinate, is about the u direction. So the pixel value I should be this one, because that's the one that is multiplied by the u vector in SU direction. All right, so I hope it's clear now. But even I confuse these things. I mean, as long as you're consistent within yourself, this shouldn't matter that much. But what this means, the impact of such a thing is that when you write your images, given the pixel coordinates ij, when you're writing them as a ppm file, you need to be careful. Otherwise, you're going to have a sideways image or something else. Okay, so while you're writing your image as a ppm file, the ppm file actually stores them row-wise. So if you have a for loop going from I to, the outer loop is I, you will be writing actually column-wise. You have to be careful when writing your images. And the final ray equation is simply E plus, if we find the coordinate of the center of this pixel as S, S minus E will be this vector. Okay, look at this vector. This S, this is E, S minus E is this vector, and E plus S minus E, T, will be our ray equation. Since the length of this vector is S minus E like this, which is going to be when T is equal to 1, we will be exactly at the coordinate center of the pixel. So that's why we will be interested in object intersections in which T is greater than or equal to 1.0. Okay, if this vector is normalized, then we need to do something else. I mean, if we normalize this vector, if it's just a direction like this, T maybe actually have to be larger than something else. Okay, so we don't want to normalize this vector. This direction vector, when we don't want to normalize it. We just want to show it as it is, because when T is equal to 1, I want to be here, and when T is equal to 0, I want to be here. That's why I don't want to rescale this vector. All right, now, actually, I have like 20 or so minutes left. I'm going to quickly go over, I'm going to come back to ray object intersection next week as well, but I want to just quickly skip over them to tell you what kind of a thing we are going to do. We are going to derive the equations, but I just want to show you directly the code for that and what kind of a ray tracing, because these things, when they're on the slides, they seem like abstract things. They're just mathematics, bunch of vector algebra and such, right? I mean, actually, when you code them in a program, you will see that they work. Okay, try to do that yourself, and then it will be really rewarding to see actual images forming up as PNG files or PPM files. So you can also try this example in which the I is at the world origin. Our U and V axes are the world X and Y axes, so the camera is very nicely set up. And NX and NY, this is the images like this, and it's a square image. Okay, as you can see, it's a 2x2 image in terms of width and height, not in terms of resolution. Its resolution is 124 by 768, so it's a rectangular image like this. Okay, so 124 pixels here, 1024, 768 pixels here, so it's an approximately 1 megapixel image, and the distance and the image is exactly at z is equal to -1. Look at this equation. This is a plane equation in 3 dimensions. Z is equal to -1 is a plane equation, and that's actually my image plane. Why z is equal to -1 image plane? Because my I is at 0, 0. I'm looking at -w direction. If you go 1 unit in the -w direction, you will hit the z is equal to -1 place. Exactly. Gaze vector is 0, 0, -1. Okay, 0, 0, 1 is the w vector. Gaze vector is reverse of that. So gaze vector is 0, 0, -1, and the distance is 1. Hence, image plane is going to be at z is equal to -1. Okay, so I'm going to be skipping this. Then after we have the ray, the remaining thing is to intersect the ray with the objects. Okay, and for objects we have a sphere. I already talked about parametric lines. We have our ray equation. Ray equation is a parametric line itself. Okay, the way we are going to do is, for example, I can actually talk about this. Not on the slide, because as I said, I want to show you my code. I'm going to quit this PowerPoint, this card, and I'm going to open GIMP. GIMP is here. Okay, now imagine we have a sphere. How do we represent a sphere in 3D? With a center and a radius. Okay, representing a sphere is really easy. Center is a three-dimensional vector. It has Cx, Cy, Cz components. Cz, okay, it's a three-dimensional vector, and it has a radius. That's what a sphere is. Okay, and what is the equation of a sphere in 3 dimensions? So all the points around that in 3 dimensions. Okay, so this is a sphere, not a circle. It lives in 3 dimensions. The points on the sphere are actually all the points which are equidistant to the center. Okay, which means that if I have a point P, if I take this vector P minus C, this is a point P here. If you look at this P minus C vector, if you take a look at its distance, it has to be equal to R, right? That's the sphere equation actually in 3 dimensions. That's the implicit sphere. All the points that satisfy this equation are my sphere points, are my points on the sphere. So, so these are all vectors. This is a scalar. What is this distance? Basically, it's basically say that px minus cx squared. So this normal indicates the length of this is the length of this vector p minus c, which is simply given by py minus cy squared plus pz minus cz squared square root. This is equal to r. Okay, if you take the squares of both sides, get rid of the square root, you get your familiar sphere equation in 3 dimensions. Oh no, in this representation, our sphere is not triangles. We will represent, in this ray tracing algorithm, we will represent spheres as continuous objects, that live on 3 dimensions with this equation. So they will have infinitely many points on them. We will represent spheres with infinite resolution. They are not made up of triangles. They are made up of this equation. Now, when I have a ray, how do I intersect my ray with the sphere? What is the ray equation? My ray equation is this point P this time is equal to, starting from I, going in some direction D, which was S minus E, if you remember. So D here is equal to S minus E, where S is the center of the pixel. Okay, now, if I plug in, if you look at this is actually, this PT is 3 equations. It has EX plus DXT. Its X coordinate is this. Its Y coordinate is this, DYT. And its Z coordinate is this, DZT. Okay, so X, Y, Z coordinate of my point, PX, PY, PZ. Okay. If you plug in this px, py, pz here in this equation, okay, if my line intersects with this, I plug in this px, py, pz here, everything here is known. Ex, ey, ez is known, dx, dy, dz is known, center of the sphere is known, radius of the sphere is known. The only thing that is unknown in this equation is t, all right? So I have one quadratic equation with one unknown. So at the end, the equation will have a form that looks like this. At squared plus bt plus c equals 0. Okay, so it will have a form like this. And you are going to compute the delta b square x minus 4ac, right? This was delta. If delta is negative, what does it mean? There are no real roots. What does it mean? There are no real roots. It means that my line or my ray does not intersect with the sphere. If delta is greater than 0, it means that there are two intersection points, and I solve for T1 and T2, and I pick the smaller one. I pick the small. If my ray is in this direction, I pick the smaller one. If this is T1, this is T2. If delta is equal to 0, it means that my line or ray is tangent to the sphere at a single point. You can determine yourself whether you would see such a sphere or not. You can actually take this tangent point as the intersection point. Now, this is how we will do the intersection. Intersection with triangles is also simple. We will try to intersect with the ray with the plane equation. There are two methods which we will describe later, but in the last 15 minutes I want to show you my code. All right, so here in my Windows system I have the WSL, Windows subsystem for Linux, something like that. So the good thing is that Windows really Microsoft, they outdid themselves. So there's a question, intersect point, which normal towards the focal point on the sphere or closest to focal point. So we are going to use whatever T1 is smaller, that will be our intersection point. Okay, then the normal vector is something else. If you know the intersection point, for example, if this is your intersection point, the normal vector is actually this. Okay, the normal on the surface of the sphere at this intersection point may be something arbitrary. For example, if you're intersecting at this point, the normal vector is this. If you're intersecting at this point, the normal is this. Okay, so the normal on a sphere is actually very easy. But we will come to the normal vector when we try to compute different light amount. What is the light amount? For example, if this is a red sphere, and if there's a light here, not all the points on the sphere will be the same amount of red. Some of them will be bright red, some of them will be dark red. Okay, and I'm going to show you actually how we can do that. So this, Windows subsystem on Linux, I've installed Ubuntu on my Windows, which is very nice. It's much faster than a virtual machine actually. What I did before, 10 minutes before the class, I installed ImageMagick by using this apt install ImageMagick. Okay, so this installed the ImageMagick tool set. Installed it 2 L's. Okay, so there's this Ubuntu package also as ImageMagick, and it comes with a bunch of tools. One of them is convert. It can convert between many different file formats, image formats, and because I wanted to convert my PPM image to a PNG image, that's why I use this convert. I also figured out that after I installed this Ubuntu, I just noticed that I didn't have any C compiler in it, so I also installed all the C compilers and the debuggers with build essentials. So if you install this build essential, you can have your GNU C compiler along with it. So this is my program. Let me show you quickly. This is the version 1. Let's look at the main function, what it does. Okay, so let's here. So if you look at the main function, it reads two files, the camera and the scene format. We are going to come to that later, but the camera, basically it shows where the eye point is, which direction we are looking at, what's the up vector, and things like that. And the scene file, they are very small files. Let me just show you. Simple camera. This is the camera file. Okay, it tells you that the camera is located as 0 to 40. This is, I think, 0, 0, -1 is its up vector or the u-axis, whatever they are. You need to know the format. This is not structured at all, and it doesn't tell us which parameters are. They're not in the file, so you need to know yourself how you are going to treat the format. But one of them should be gaze. I think this is the gaze, and this is the up vector. I just gave regular things, and these are L, R, B, and T values, or or maybe this is, yeah, this should be L, R, B, and T values. This is our image window. This is the distance, 3 units, and this is the NX and NY, the resolution of the image, and the name of the image that to write. Okay, so the camera description is very simple. If we take a look at the scene, simple scene, sorry, it's like this. It basically tells us that, okay, so what does this tell? Again, I'm going to guess what this means, but I think there are 3 spheres. Yeah, there are 3 spheres here. I don't know what these are. Maybe these are some triangles. Yeah, there must be some triangles with some coordinates. But I'm not using them at all. I think I'm just using the spheres, the 3 spheres with different values. But basically, these are just, all I need is the representation of a sphere by its center. Okay, the center of the sphere, its material color. For example, this probably is RGB, red, green, blue. So I have a red sphere and a blue sphere. This is the color of the blue sphere, and this is a yellow sphere. RG values are 255, so a yellow sphere. I have 3 spheres here that I'm going to do, and these are, I think, some triangles, but I'm not sure. Because I'm in my first simple ray tracer, I didn't use any triangles, just the 3 spheres. Now, let me just show you the code again in the last 8 minutes or so, and I'm going to execute it and see what it looks like. I'm going to overall tell you which functions are there. The first thing is, okay, let's look at the init image function, what we do. In init image, it's very simple. I have an image here of size X, size Y, and I reset all the RGB values to 0. So where did I initialize this image first? So an image, on my image, is a 2-dimensional color array. An image is nothing but a 2-dimensional color array, and color is this simple struct with just integer RGB values. Okay, so this is what color is, just a 3-dimensional vector of int to have RGB values. And my image is nothing but a 2-dimensional array of 2-dimensional matrix of colors. And the way I initialize this image, first I actually I allocate enough space for the number of pixels in a column, and then I allocate every row separately. So I just set up, I mean, this is just pure C. I mean, you could have done this easily with C++ dynamically also. So lots of additional code which is not needed actually. You can have a size X by size Y image of colors. That's it. And we initialize with just black color. Okay, so it's initialized with black color. Now, for example, if you initialize it with white color, if you want to initialize the background with white, you can actually do something like this. Now the background will be white. Okay, after we initialize, let's go back to this init image. So what I do is I have some hard-coded light source in my ray tracer. This is the light's position. I have a light at the top, 0, 20, 0. At coordinate 0, 20, 0, I have a light source. And here's the ray tracing algorithm. What do I do? This is my main loop for every pixel. This is basically saying for every pixel, we generate a ray that pass through that pixel. And these are just values to keep track of the minimum intersection. For all of the spheres in my scene, look at this for loop. For k is equal to 0, k is less than number of spheres. For all of the spheres in my scene, find the intersection point, find the t value of the intersection point by intersecting my ray with that kth sphere. If the intersection is greater than 1, what does it mean? It means it's in front of the image plane. And if it is less than t min, it means that because you may have an intersection, but if another object intersected with it before, I don't need this intersection. So I basically, with this for loop, as you can see, I keep track of the minimum intersections t value up to now, which is in front of the image plane. So there are two constraints. There has to be an intersection in front of the image plane with t greater than 1, and the intersection should be closer to t min. By the way, this 40,000 is real arbitrary. I mean, if you have a single object that is actually farther away, more than 40,000 units away, this program has a bug. I mean, it won't display that object because that's actually farther away. It will not be less than t min, right? I mean, that's a small. I mean, if you have these constants, this t min, you can consider this as a far plane. Any object larger than 40,000, you just assume that you won't see them, maybe. Okay, so that's it. I mean, it's this simple. With this single for loop, the intersect, and this intersect sphere, it's actually the implementation of this. Okay, what I have written here, this is the ray, this is the sphere center, and finding this quadratic, finding this delta thing, that's what that intersect sphere is. If you go there, you'll see intersect sphere. Yeah, ABC delta, sphere center, sphere radius. That's it. And this is the CAB coefficients of that A t square bt plus c is equal to 0. This is what delta is, b squared minus 4ac. If delta is less than 0, return -1. So -1 is also like a flag that there's an intersection behind, which you're not interested. If delta is 0, you return 1t. Otherwise, you compute 2 t's and you return the smaller of those t's. Okay? And this is triangle intersection. We don't want to take a look at that. Let's go back to the main point. And that's it. After we have the intersection, what we do is we are going to see this part next week. If the closest object is not equal to -1, it means that if our ray actually hit a real object, because if the closest object is -1, I mean, this is the closest object ID, which I initialized to -1, indicating that if I don't hit any object inside this for loop, it will remain -1. So it means that my ray doesn't hit any object. So whatever the background color is, it will remain there. So this part, we are going to look at these, only like 8-10 lines of code. We are going to learn this next week. And it's just vector algebra, okay? The light diffuse component. And after that, this is the ambient component that I edit. I just manipulate whatever the color of the sphere is. I multiply it with this diffuse component that I compute with respect to the normal vector on the surface of the sphere and the light position. By using the light position and the normal vector of the point on the sphere, I do this. And I dot product these two vectors that will tell me how much light is reflected at that point. We are going to see the theoretical details of this part of the code next week. But the only thing I do is, if I see that object, I use that closest object and I change my image RGB values based on that, and that's it. Write image out file name, goes over the image array and writes them to a ppm file, and I call this convert function of convert utility of ImageMagick to convert my ppm to a PNG. So let's run this and let's see what will happen. Let me compile it. Version 1, where's version 1 compile? So I compiled it earlier. So yeah, it's compiled. So when I run it, version 1, it requires a camera file, simple camera, and you can actually use it to even visualize more complex scenes. Simple scene, I cannot see, yeah, simple scene.txt. Yeah, it ran. Okay, it finished. What it did was, it created a PNG file here. If you take a look at that, these are these three spheres. Okay, so now we are looking at a virtual world without camera. For example, would you like to put the camera a little bit up and see what will happen? Simple camera.txt. So where's our camera location? The camera location is, what was it, 2. What if I do it 3? And what if I, yeah, should I have a, what if I also have a Z component? I'm now looking at a tilted angle. Okay, if it was up was like this, maybe -1. because I will not be able to see anything. So I just changed some camera parameters. Let's see what will happen. I put the camera a little bit up, and I just run the program again. Let's reload this PNG. Let's see. I'm not sure what I'm going to see. Yeah, I don't think anything changed. Maybe it didn't. I didn't modify it. Maybe, I mean, the modification with it was really not that visible. I will share this and the ray tracer code with you, so you will be able to play with it. Play with the scene file. I will put it in AutoClass. But as you can see, it's very simple, and at the end, it's really rewarding. You can take a look at your virtual world first time from. Yeah, actually, it maybe appear tilted slightly. Maybe actually, if we even make the camera more up, like 8. Let's see what will happen. I mean, if you cannot see any spheres, that's okay. Yeah, it's tilted. As you can see, we're now looking from up. So we're actually moving the camera. You can, by playing with that image parameter and camera parameter, you can actually provide yourself an animation. You can put those PNG images one after another, produce a movie of walking around or flying through over these spheres. But actually, yeah, we have a virtual world, and with our camera, we are able to take pictures of that virtual world with this simple code. Okay, so I'll have to finish now to attend this conference. That's it for today's lecture. If you have any questions, you can email me. As I said, I will share this code with you and the simple scene and simple camera on AutoClass, all sections. Oh, for the recitation, Bilgin is going to use something else. I'm not going to give the recitation myself. Okay, so Bilgin actually is going to be using, I think, if he has a WebEx account, or if he's going to be using Zoom. So recitation is going to be in some other link. All right, so I use this link only for my lectures. Recitation is going to be given by Bilgin. So Bilgin should tell you the link to the recitation meeting. Okay. All right. Thank you, everyone. See you on Monday. See you all on Monday, and we are going to continue with ray tracing. Bye-bye.